Hi, welcome to AP Physics AP Physics 1, Unit 5, Momentum. This is the last video of this unit. This is called the ballistic pendulum. So a ballistic pendulum is a very important object to study because it actually takes the last two ideas, the conservation of energy and the conservation of momentum, and puts it into a single object so that we can study it. So the ballistic pendulum is a simple device used to measure the momentum of a projectile. Really what it's used to measure is actually the muzzle velocity of a weapon. The momentum data is then used to determine the projectile's velocity and kinetic energy. It was invented to help study or advance the study of ballistics. It is a device that, as I mentioned, it uses both conservation of momentum and conservation of energy. And the way we look at it is there's three parts to the swing of a ballistic pendulum. Okay, so the first part is the launch. And the launch generally use conservation of energy. Okay, there are parts of momentum here as well, because the way you think about it is the motion before it's striking the block we do a little bit of momentum analysis. So actually the launch part has both, and specifically the launch here would be if let's say I have a spring-loaded little toy gun, right, or toy, whatever. You pull the trigger, a little spring activates, and then out comes a speed, or out comes a projectile at some sort of speed. So you can use a conservation of energy analysis to figure out how fast did it come out of the little toy, and then it's going to move through the air, strike a block, which now we have, and I put it as an inelastic collision, but this can be really any collision, and so this will use conservation of momentum. Okay, so if it's inelastic, remember, and that can be here, most cases the object's going to embed into the block, but if it doesn't and it bounces off, right, you could have an elastic collision occurring, which will actually give you the most in terms of energy, because remember, energy is conserved in that process. When you have inelastic collisions, the energy is not conserved, so then you have less energy coming out of the collision than was going before the collision. And then finally you have the swing, and that will use conservation of energy. Right, and so there's a really cool device that's used in labs where you have a little spring-loaded part of it. You pull the little trigger they have, out shoots a ball, a sphere, embeds into a hanging device, and then it swings up. And then as it starts to lose the energy, and as it swings back, there's a little hook that catches. And what you're allowed to do with that hook is measure the angle, right? And then you can kind of work your way backwards to figure out how fast did we shoot that object out. Oh, I put a 0 and I shouldn't be a 0. Okay, and that would be our question mark. Okay, so you may work from launch, collision, swing, or you can go swing, collision, launch. Excuse me. So let's look at an example problem using the ballistic pendulum. And so here we have a 10-gram bullet fired into a 1,200 gram wood block hanging from 150 centimeter long string. The bullet embeds itself into the block, and the block then swings out to an angle of 40 degrees. What was the speed of the bullet prior to impacting the block? So we don't have to trace it all the way back to the launch. All we're going to do here is the swing and then the collision. And it says it embeds, so we will have a perfectly inelastic collision. And so what that tells us is that after the collision, the bullet and block will move off at a common velocity, but prior to the collision, it'll just be the bullet, because remember, momentum is always conserved in collisions, and ultimately that's what we're going to look for. But the first thing we need to find is, what is VF, right? What is the final velocity that they're going to be launched at? But where does that come from? Well, that comes from the swing, right? So the final velocity needed for the collision is the initial velocity going into the swing. And so that's the first thing we need to solve for. Now, they tell us that it'll swing up to 40 degrees. So here's our, bullet block. And so they're saying that this is 40 degrees. So the first thing we have to use is our little shortcut equation we learned back in Unit 4 to find the height. So we're going to do 1.5 minus 1.5 cosine 40. And it gives us a height of 0.351 meters. So that if this is my h equals 0 point down here, right, I've traveled up 0.351 meters. And now I use my conservation of energy, so delta E equals 0. Now, the last part of my swing, all I have is mgh. The first part of my swing, I have 1/2 mv initial squared. And that's what we're going to look for, because that's this right here, which then becomes the final velocity. And so we get our classic root 2gh equation to find the speed. So we have square root of 2 times 9.8 times h, which is 0.351. Okay, take the square root of that, and we get an initial velocity of 2.6 meters per second. So this is 2.6 meters per second, which means this is 2.6 meters per second. So you can see how it's all connected. The initial velocity from the swing becomes the final velocity from the collision, which now we can trace it back to what was the initial velocity of the bullet. So we're going to say velocity of bullet is m bullet plus m block times that final velocity we just calculated, divided by the mass of the bullet. Now the good thing is, since everything is in grams, you can leave it in grams, because if you look at it, we'll have grams over grams. Okay, so we do 10 grams plus 1200 grams times 2.6 divided by 10. Plug it into our calculators, and we find that before the collision, before it strikes the block, the bullet was traveling 315 meters per second, which is almost near the speed of sound. The speed of sound is 343. Now that's at 20 degrees Celsius, because sound is a pressure wave and it does vary based on temperature. But that's how fast the bullet is traveling. So we've made it to the end of Unit 5. The next unit is going to be Unit 6, which is simple harmonic motion. And then we have, only after that, you have one more unit, and that's going to be on rotation.